In the last lecture, we had written down the Schrodinger equation in 3 dimensions for a particle in a central potential in spherical polar coordinates. We had then introduced the separation of variable ansars, in which we had written down the wave function as a product of a radial function and an angular function y of theta and phi. After taking a look at the deeper connection between rotational symmetry and the angular equation that we had obtained, we then went on to further separate this y theta phi into a product of a function of theta and a function of phi and set up the corresponding ordinary differential equations. The phi equation was simple enough to solve. The theta equation, after a substitution of variables cos theta equals z, gave rise to the associated Legendre equation, which is simply a generalization of the Legendre equation which many of you had met in past courses, maybe in electromagnetism. We had finally described why trying to solve the associated Legendre equation directly by power series method is not such a great idea, and in today's lecture we will start from there. As it turned out, the problem really was due to the fact that there is a difficulty which arises due to the potential divergence at z equal to plus minus 1, which are regular singular points of the associated Legendre equation. As always, it's a good idea to get to know your enemy well, which is you need to know exactly how the solution should behave close to these singular points. Let us now turn to the task of finding out the behavior of the solutions to the associated Legendre equation close to the singularities, that is, close to z equal to plus 1 and z equal to minus 1. I'm going to show you how to do the z equal to plus 1 case now. The z equal to minus 1 case can be done with a very similar kind of treatment. So the easiest way to understand the behavior close to z equal to plus 1 is to substitute in terms of a new variable. Let's bring in z equals 1 minus u so that the derivative will be of a different sign, and 1 plus z is obviously 2 minus u. Plug all of this back here. The reason why we are doing that is that it's always easier to investigate what happens close to 0, because that's easiest to see. So z going to plus 1 of course means u goes to 0. So we have just changed or shifted our variable so that the singularity now sits at 0. If you do that, of course, 1 minus z square is 1 minus z into 1 plus z. 1 minus z is simply u and 1 plus z is 2 minus u. So we just put that in everywhere. And now this is the equation we have. And we want to investigate the behavior of solutions to this equation when you are very close to u equal to 0. So what we will do is we are going to work out things this way. Notice that despite the fact that u equals 0 is a singular point, it's a regular singular point, which means that we can have a solution which looks like a power series except that it may have a pole there. So basically you can try solving this using the Frobenius method. I don't even have to work out the entire Frobenius calculation here. All I need to work out is what happens very, very close to u equal to 0, and there the lowest power will dominate. Or lowest power here means the largest negative power, if the power is negative at all. So even if only positive powers were there in the solution, the lowest power of u will be the largest when u is close to 0. So let us say f can be written in this form, u to the rho plus higher order terms. This of course is the beginning of the Frobenius solution. I'm simply not going to worry about the higher order terms, but if you plug in u to the rho plus higher order terms in this equation, what you can easily see is that the lowest power of u that the left hand side will have is rho minus 1. Why? Because this becomes u to the rho minus 2, but because of the presence of u, this term will give you u to the rho minus 1. The next one will give you a higher power, so we are not bothered too much about that. This term will give you u to the rho minus 1, and f by 2u will give you e to the rho minus 1. So if you just gather together what you have at the lowest power of u, which remember is a dominant term on the left hand side, what you are going to get is, from this term you are going to get a 2 times rho into rho minus 1 from the differentiation. From this you are going to get a 2, which is just 2 into 1. Remember the u you don't consider because that gives rise to a higher power. So 2 into 1 times rho from the derivative. And here, this will give you u to the rho, but so we simply don't consider that because that's a higher power compared to u to the rho minus 1. And here the 2 minus u, for very small values of u, of course, can be approximated by 2. Or you can think of this as taking the 2 out and writing this 1 minus u by 2 as an infinite power series. 1 minus 1 by 2 to the power minus 1 as an infinite power series. But whether you do it that way or simply approximate u by 2, you get the same result, that at the u to the rho minus 1 order, you get minus m square by 2. And since every coefficient has to vanish, this coefficient of u to the rho minus 1 also has to vanish. This is what we would have done to find out the indicial equation for the Frobenius method. But it really means much more than just finding out the index. The reason why we are focusing on the lowest power is because that's the term which dominates when you come very, very close to u equal to 0. Now notice that if you equate this to 0 ultimately, what you are going to get is rho square must be equal to m square by 4. That means rho has to be plus minus m by 2. So now you see that the behavior of the function f very close to e equal to 0 is dominated by either 1 minus z to the power mod m by 2 or 1 minus z to the power minus mod m by 2. I have deliberately written the square root of m square as mod m and not as m, just to emphasize that this solution is pretty nicely behaved as z tends to 1, because this power is a positive power, whereas this solution diverges when z tends to 1. Now, similarly, as z approaches minus 1, you could carry out the same calculation, replacing 1 plus z by a new variable and carrying the calculation through. What you will see is f, the function, will behave like 1 plus z to the power mod m by 2, which is the well-behaved solution, or 1 plus z to the power minus mod m by 2. So notice that while one of the two behaviors is decent, stays finite, in fact goes to 0 as z goes to plus or minus 1, the other solution actually blows up. And that is something we always knew could happen because of the regular singularity which the equation has at z equal to plus minus 1. So if you combine the behavior at both z equal to plus 1 and z equal to minus 1, the one which is decent or which is good for us is a product of these two behaviors. So we would like to find that solution to the associated Legendre equation which behaves like 1 minus z square to the power mod m by 2 as z goes very close to plus minus 1. But we have to remember that there's always a chance that we might end up with a solution which has the behavior 1 minus z square to the power minus mod m by 2, a divergent behavior as z goes to plus minus 1. And that's the one we have to avoid at all costs. As a means of avoiding the potential trouble as z goes to plus minus 1, we will do exactly what we did in the case for the harmonic oscillator, where we took out of the two possible behaviors at plus minus infinity the factor e to the minus z square by 2. Here we will write capital F of z as 1 minus z square to the power plus mod m by 2 times g of z. So this is the behavior at z equal to plus minus 1 which we want. And this factor in front will ensure that we do have a solution to the associated Legendre equation, but we hope that this is not going to destroy the nice behavior imposed by this factor. But let me warn you at this stage that because we know that f of z has two choices, it can either behave like this as z goes to plus minus 1, or it can behave like 1 minus z square to the power minus mod m by 2. There's every chance that the g of z might end up behaving like 1 minus z square to the power minus mod m So that despite the presence of this nice factor in front, f of z would still diverge like 1 minus z squared to the power minus mod m by 2. So this is the kind of possible behavior for g of z which we have to be on our guard against. The next step is, of course, to find out the differential equation which g of z obeys, and that's pretty easy to do, although a bit laborious. The trick is to write f of z as 1 minus z squared to the power mod m by 2 g of z, then differentiate it, and you of course end up with two terms, one coming from the derivative of 1 minus z squared to the power mod m by 2, which is this term, and the other coming from differentiating g of z, which is of course this term. Now, you can actually simplify your calculation somewhat by multiplying through by 1 minus z squared, which will give you a 1 minus z squared to the power mod m by 2 factor in both terms. This of course will have an extra 1 minus z squared, so that's why you get 1 minus z squared dg dz, and this term becomes minus mod m zg. Now if you differentiate this expression further with respect to z, you once again get two pieces. In one piece, you keep this intact, differentiate this, which gives you 1 minus z squared d2g dz2 minus 2z dg dz from differentiating the 1 minus z squared. You also get minus mod m z dg dz by differentiating g here. So we have combined the two in this term. And in addition to that, you get another term by differentiating the z. So you get minus mod m g. So this is one of the pieces which you get by differentiating this term in the bracket. The other piece, of course, is what you will get by differentiating 1 minus z squared to the power mod m by 2, leaving this intact. So that's what you have here. This factor stays the same, and this gets differentiated to give you mod m by 2 times minus 2z times 1 minus z squared to the power mod m by 2 minus 1. Now let us just combine both pieces together by taking 1 minus z squared to the power mod m by 2 common. That of course gives rise to this piece here. This gets modified a bit because you also get another minus mod m z times dz term from this piece. Remember, you have taken the 1 minus z squared to the mod m by 2 already out common, and this 1 minus z squared here cancels the minus 1 for this piece. So that's what you're going to get. The rest is simply by something you obtain by combining this piece here, that's the minus mod m g, with this piece minus mod m z times the minus mod m z that you have here. Of course, the 2's cancel. And here, of course, you have the 1 minus z square. You're short 1 minus z square factor. That's why you end up with a 1 minus z square in the denominator. Now that you have this form, it's pretty straightforward to see that the associated Legendre equation, once you plug this in, simply becomes of this form. So let me reduce the gap a bit so that you can see the two together. 1 minus z squared to the mod m by 2, you have taken common. This is the whole factor that you get from this piece. To this you have to add lambda, which of course is here. And the only other tricky thing is you have to take this piece and you have to add them together. Notice that mod m square and m square are just the same. So when you add these two terms together, what you get is m square z square by 1 minus z square minus m square by 1 minus z square, which if you take m square common or mod m square common, same thing, gives you z square minus 1 by 1 minus z square. So that's just minus mod m square. And that is what is sitting here. Of course, you already had a minus mod m and you have minus mod m square extra. So this is why you get a factor looking like this. Now, the associated Legendre equation is that this left hand side is 0. And since 1 minus z squared to the mod m by 2 is not 0, the associated Legendre equation becomes this equation for g. This bracket has to vanish. Now this actually is simpler than the equation that we had, because this 1 by 1 minus z square term that was there in the associated Legendre equation has been eliminated. Of course, this equation still has a singular point at z equal to plus minus 1, as can be seen from this factor. It is still a regular singular point. And so the problem that can happen at z equal to plus minus 1 still can happen. You have not completely got rid of that possibility. But now, notice that if I try the power series solution here, this will give you z to the n minus 2, but then the terms that you will get, this one will give you z to the n minus 2. That's the power that you will get from Cn z to the n. This will give you z to the n. This will give you z to the n. And this will give you z to the n. So only two different powers will multiply Cn. And if you match the powers, you will see Cn plus 2 and Cn as a coefficient of the same power of z. So what you're going to get is a two-term recursion relation. And because of the fact that there is potential trouble at z equal to plus minus 1, having a two-term recursion relation is very, very handy, because that's exactly what is going to help you to truncate the series if necessary and avoid a solution which blows up. Armed with this assurance that we will end up with a two-term recursion relation and hence be able to handle the singularity at z equal to plus minus 1 better with this equation, we will just go ahead and try a power series solution for this. We will use the standard steps of replacing gz by the power series, sum over n going from 0 to infinity Cn z to the n, get dg dz and d2g dz2 by differentiating term by term, and then substituting these into the equation. And if I do that, I'll get this piece from the 1 minus z squared times d2g dz2, and into n minus 1 Cn z to the n minus 2 is simply d2g dz2, and this is what you get when you multiply that by z square. When you multiply dg dz by a z, you get this power series, and the twice mod m plus 1 is the extra factor in front, and finally the g times this factor simply gives you this. So when you collect everything together, you get one piece with z to the n minus 2, and all the other three have z to the n. We want to make them into the same power so that we can compare coefficients. So we change n minus 2 to n here. Of course, that means Cn becomes Cn plus 2. N into n minus 1 becomes n plus 1 into n plus 2. The lower limit should have actually changed to minus 2 here, but the n equal to minus 2 and n equal to minus 1 terms are both 0, so you don't have to bother doing that. So now you have two power series, both running from n equal to 0 to infinity. So we can simply combine them together into one. And this immediately tells us that because we want every coefficient of z to the n to vanish in order to get a 0 on the right hand side, we must have Cn plus 2 obey this particular relation. We have just done a bit of algebra here so that we have managed to write n into n plus 2 mod m plus 1 plus mod m into mod m plus 1 in this factorized form. Other than that, this is just what you get by taking this coefficient times Cn and dividing that by n plus 1 into n plus 2 after a change of sign, of course. As expected, this gives you a two-term recursion relation, and this tells you that you can find out C2, C4, C6, C8 in terms of C0, and C3, C5, C7, C9, etc. in terms of C1. So the solution will break up into two pieces, an even series with C0 as an overall coefficient and an odd series with C1 as an overall coefficient. So the combination of the two independent solutions will give you the general solution to the equation for G, and that will lead to a solution to the associated Legendre equation. However, as we had pointed out repeatedly, there is a potential problem that this solution may diverge as z goes to plus minus 1. So let us examine whether that is what happens. We can quickly see that the ratio Cn plus 2 by Cn approaches 1 as n goes to infinity, which means the power series definitely converges for mod z less than 1. Now that shouldn't come as a surprise. If you're starting at z equal to 0, which is the center of your power series, you're expanding about z equal to 0, then the nearest singularity of the equation is at z equal to plus 1 and z equal to minus 1. And that means that within that distance, the power series is bound to converge. But we are concerned with what happens at exactly z equal to plus 1. And there, unfortunately, the infinite series will diverge at both plus 1 and minus 1. And it will diverge as 1 minus s squared to the power minus mod m. How do we know that? Well, to see that, what we need to do is take a look at what happens for very large powers of z. Remember, a divergence in a power series can only occur from the tail of the power series, from the very large powers. The initial finite number of terms in the head of the power series, no matter how large they are, they will never give you a divergence. They will always add up to some finite number. To investigate divergence, you have to look at what happens for very large powers of z. In other words, for very large values of n. And what does Cn plus 2 by Cn behave like for very large values of n? To see this a bit more carefully, we not only divide through by n square, but rather than taking the limit directly, we take a look at what happens at the order of 1 by n as well. So it's pretty easy to figure out that the twice m mod m plus 1 into n term after division by n square gives you this, plus higher order terms. In the denominator, you have 1 plus 3 by n. And if you quickly combine the two together, you find that for very large n, if you ignore higher order terms, Cn plus 2 by Cn ratio is 1 plus twice mod m minus 1 by n. And you can easily check that the infinite series for 1 minus z squared to the power minus mod m has exactly the same behavior at very large n. So for very, very large powers of z, both the series that we have and the series for 1 minus z squared to the minus mod m have the same behavior. So when one series diverges, the other series diverges in the same manner. So we are in trouble here. How do we get out of the trouble? Simple. The way to get out of the trouble is stop this from being an infinite series. That is, you have to truncate the series. And as with the harmonic oscillator case, I don't really need to repeat the entire argument there. It's possible to get solutions which converge at one end of the power series, one end of the interval, without truncating. But because one of the solutions is even and the other one is odd, if you try to make the divergences cancel at z equal to plus 1, they will only add up at z equal to minus 1. So the only solution is to truncate one of the infinite series, and for the other series, which then would definitely have diverged, set the coefficient to 0. So truncation is the way ahead. To truncate the power series so that it yields not an infinite series but a kth order polynomial, we have to choose lambda in such a way that for some k, which is either 0, 1, 2 or any non-negative integer, ck will be non-zero, but despite that ck plus 2 will be 0. And remember, if once ck plus 2 is 0, ck plus 4, ck plus 6, ck plus 8 will all vanish from this recursion relation. That is the advantage of having a two-term recursion relation. Once you get a 0, all subsequent terms vanish. At least all subsequent even step terms vanish. That means that what we are demanding is lambda must take a very specific form. Lambda must be of the form k plus mod m into k plus mod m plus 1, because only that will make the numerator here vanish for n equals k. And k, remember, has to be a non-negative integer. This implies that lambda has to be of the form L into L plus 1, where L is k plus mod m. So L is mod m or mod m plus 1, mod m plus 2, and so on. So L is actually a non-negative integer larger than or equal to mod m. Remember, we had a very similar result for the Legendre equation also, and that's the one which you are familiar with. There you saw that L can take values 0, 1, 2, etc. But also remember that that case was for m equal to 0. So with this choice, gz is a polynomial of degree k, where k is L minus mod m. Of course, that's one of the two solutions. The other solution is an infinite series still, and that will diverge as z goes to plus minus 1. That's the one we are going to ignore. Remember that despite having the 1 minus z squared to the power plus mod m by 2 in front, that solution would still diverge badly because g of z ultimately will behave, if not truncated, as 1 minus z squared to the power minus mod m. So the well-behaved solution for f of z as z goes to plus minus 1 is 1 minus z squared to the power mod m by 2 times g of z, where g of z is this finite polynomial of degree L minus mod m. And this solution is called the associated Legendre function. Some sources, including Wikipedia, call this the associated Legendre polynomial. I don't really like that term because it seems to imply that this is a polynomial, which of course it is if mod m is an even integer, but for an odd integer mod m, this really is an infinite series and not a polynomial, because of the fact that it has powers of square root of 1 minus z square in front. We can certainly determine these polynomials, g of z, simply by making use of the recursion relation between coefficients that we have just derived. But there is a very nice connection between these polynomials and the Legendre polynomials, and that is what we are going to explore now. Remember, the Legendre differential equation is just this second order differential equation. 1 minus z squared due to PL dz2 minus 2z dPL dz plus L into L plus 1 PL equals 0. And if L is a non-negative integer, then one solution to this equation is a Legendre polynomial, which can be also written down as this term, that is, the Lth derivative of z square minus 1 to the power L up to a factor of 1 by 2 to the L factorial. Now what we do is we differentiate the Legendre equation itself m times, or rather mod m times, since you have to differentiate it a positive number of times, with respect to z successively. And here we make use of Leibniz rule for successive differentiation. For example, when we differentiate this product here, we have one term in which we don't differentiate this at all, differentiate this term mod m times, another term in which we take mod m c1, the combination factor, the same factor that you have in the binomial theorem, differentiate this once to get minus 2z, and differentiate this mod m minus 1 times, and one more term where you put in mod m c2 as a factor overall, differentiate this twice, differentiate this mod m minus 2 times. Of course, the Leibniz rule tells you that you have to keep on differentiating more and more terms, that is more and more number of times. But in this particular case, because the factor 1 minus z square vanishes when you differentiate it more than twice, the formula just stops there. Well, doing something similar, we can get this equation. The first three terms are what you get by successively differentiating this product mod m times. The terms in blue are what you get when you differentiate this product 2z dPL dz mod m times. So the first term, for example, is where you don't differentiate 2z at all, but you differentiate this mod m times this one to get d mod m plus 1 dz mod m plus 1. The next term is when you differentiate minus 2z once to get minus 2, and differentiate this mod m minus 1 times, and you get a single combinatorial factor. Finally, this last term is very simple. L into L plus 1 is just a factor. It just goes out and you have a mod mth derivative of PL. Now, if you just combine all these terms together, taking into account the fact that mod m c1 is of course mod m c2 is mod m into mod m minus 1 by 2 and all that, and do a bit of algebra, you will find that the equation now becomes this, and this should begin to look very, very familiar. In fact, this should immediately show you that if you take the function d mod m PL dz mod m, that is the mod mth derivative of PL, then that satisfies the second order differential equation, which is exactly the same equation that we had been solving for G. Now the second order differential equation has two solutions, as we have just seen. One of them is a polynomial of degree L minus mod m, the other one is an infinite series. This is of course a polynomial of degree L minus mod m, so it has to be the function that we used in defining the associated Legendre function. So at least for positive m, what we can always do is define the associated Legendre function in this manner. We differentiate PL m times with respect to z, multiply this by the factor 1 minus z squared to the power m by 2. This of course is the g of z that we have in the definition. This is the 1 minus z squared to the m by 2 factor that was there to give me f of z. And in front of all this, we put in a factor of minus 1 to the m. This is called the Condon-Shortley phase, named after the textbook where this phase appeared, and which has made this phase the standard thing to use in every quantum mechanics text since then. Let me warn you that when the associated Legendre function is used in other branches of even mathematical physics, the authors may or may not use this minus 1 to the power m phase. Some authors omit a phase completely, some authors put in some other constant factor in front of this. Now while this formula makes sense only for positive m, or rather non-negative m, we can actually extend this to hold for negative m as well, simply by making use of the Rodrigues formula for PL. What we do is we introduce the Rodrigues formula in this expression, and then PLMZ becomes this. Notice that now what we are doing is we are differentiating the function z square minus 1 to the L plus m times, and since L is always mod m or more, L plus m is always positive or rather non-negative, irrespective of whether m is positive or negative. So this is a genuine repeated derivative which can be actually worked out. So this formula works no matter whether m is negative or positive. At least the formula is sensible. However, let me point out one thing. The equation which gave rise to the associated Legendre function was the equation for capital theta that we had derived earlier in this lecture. And in that equation, m enters only as m square. What that means is plus m and minus m lead to exactly the same equation for capital theta and hence for capital F, the equation that we ultimately solved. So the question that can arise in your mind is, how then can we get two solutions for PLM and PL minus m? Now of course you might say that because this is a second order differential equation, it does have two independent solutions. So maybe one of them is PL plus m and the other one is PL minus m. But if you think about it a bit, one solution and only one solution is supposed to stay well behaved as z goes to plus minus 1. The other solution would not stay well behaved. And it is rather unlikely that the PLM that I am getting for negative m here is actually a solution that blows up as z approaches plus minus 1. In fact, it turns out that you can show with a bit of algebra that PL minus mz is actually related to PLMZ, is not an independent function, is just proportional to it. And this is the proportionality factor. It's really quite easy to show this. I will perhaps set this as an assignment to solve. Another important nice property that we have is these PLMZs actually have a definite parity. If you replace z by minus z, it's pretty easy to see from the formula that we have here that this 1 minus z square factor of course does not change, neither does this z square minus 1 to the L. The only thing that changes is the dz. We change the sign. So if you change z to minus z, PLM will pick up an overall sign of minus 1 to the power L plus m. Now the associated Legendre functions have many interesting properties. And some of these will be used in the course of this lecture. We will not list out all the properties here. After all, you can always look them up in a textbook. But we will point out one, and that is the orthogonality relation which PLMs obey. Now, this is slightly tricky in the sense that PLM and PKN, if you take two different associated Legendre functions with different values of L, K, M and N, then they are usually not orthogonal to each other. So this is a departure from the kind of functions we have been seeing so far. For the Legendre polynomials, the integral from -1 to +1 with respect to z vanishes whenever you are using two different Legendre polynomials. For the associated Legendre functions, on the other hand, the situation is a lot more complex, and the orthogonality actually comes in a rather different manner. Only when you use the same m for both the functions but different l's, so we are using PLM and PKM, and integrate this from -1 to +1 with respect to z, you are going to end up with a 0 if k and l are different. So for this to occur, you have to use the same m on both the associated Legendre functions. And in this case, if you of course use the same k as l, then this integral has a non-zero value. That value happens to be 2 by 2l plus 1 times l plus m factorial by l minus m factorial. Just as a quick cross-check, if you are talking about the Legendre polynomials themselves, m is 0, and then the l plus m factorial and l minus m factorials will just cancel, and you get back the familiar orthonormality relation for Legendre polynomials. Now, I am not going to lengthen this already long talk too far by listing out all the properties of associated Legendre functions. We will describe some of these properties when we need them in some calculation later on. For the time being, let me just round off this lecture by returning to the original theme that we had. We were trying to solve the angular equation for y of theta phi, which, if you remember, was written in terms of capital theta of theta times capital phi of phi, and we had already found out that capital phi should take the form e to the im phi, where m is some integer, and capital theta of theta up to a constant will have to be an associated Legendre function PLM of cosine theta. So this is how we define these very important class of functions called spherical harmonics. They play an immense role. As you can see from the name, they are sort of spherical analogues to the harmonic functions, sines and cosines. So that should give an idea about how important these functions really are. Let me now formally define the spherical harmonic corresponding to the parameters L and M, y, L, M, theta, phi. And this is the formal definition. As I've said, you have PLM cosine theta times e to the im phi in the definition. In addition, you have a rather nasty looking factor in front. Now let me also warn you that some authors put in a -1 to the power m here. The ones who do not use the Condon-Shortley phase in the definition of PLM cosine theta, they put in the Condon-Shortley phase here. Since we have already taken into account the Condon-Shortley phase in our definition of PLM cos theta, I will not put in the -1 to the m in this definition. Either way, the Condon-Shortley phase is there in YLM theta phi in all quantum mechanics textbooks, either via its inclusion in PLM cos theta or via an explicit inclusion here. Now, why is there this rather complicated looking factor in front of the definition? The answer is very simple. This is exactly what makes the orthonormality relationship between spherical harmonics ultimately a simple expression. And the orthonormality condition goes this way. If you take two spherical harmonics, you multiply the conjugate of one with the other. Remember, spherical harmonics are complex functions because of the presence of the e to the im phi. So complex conjugation is non-trivial here. And then integrate with respect to the solid angle measure over the entire solid angle. That means theta will run from 0 to pi and phi will run all the way from 0 to 2 pi. Of course, the solid angle measure is really sine theta d theta d phi, as you all know. Once this integral is carried out, the answer is 1 if L equals L prime and M equals M prime and 0 otherwise. Please note that while I say that PLM and PL prime M prime are not orthogonal unless M equals M prime, that is not an issue with the spherical harmonics, because the M equal to M prime orthonormality, that is, the fact that the spherical harmonic integral will vanish whenever M is not equal to M prime, is dictated by the phi integral. So ultimately you end up with this simple orthonormalization relation with a 1 in front, and that is why you have to include this factor in the definition. Another very important and interesting property of the spherical harmonics is exactly how it responds to parity operation. Remember, under parity, r vector goes to minus r vector, which means the angles theta and phi change. So the question is, what happens to spherical harmonic, which is a function of theta and phi, when you carry out the parity operation? To understand that, we first need to take a look at what happens to the angle theta and phi when you carry out a parity operation. Notice this r vector is of course the original position vector, which has angular coordinates theta and phi as indicated. If you carry out the parity operation, you get minus r vector, and what is important is that we have to pay attention to what are the angular coordinates for this minus r vector. So theta, remember, is the angle by which you have to tilt the z-axis to go through your vector. So here, the angle through which you have to tilt the z-axis to go through minus r is this angle, which is pi minus theta. So theta gets replaced by pi minus theta under parity. Also, the amount by which you have to turn the xz plane to go through r, that's phi, but the amount through which you have to turn the xz half plane, it's a positive xz half plane, remember, to go through minus r is actually a lot more. It has to be pi plus phi. So the upshot of the parity operation is theta changes to pi minus theta and phi changes to pi plus phi. So what happens to the spherical harmonics under parity? Well, ylm theta phi under the parity operation becomes ylm pi minus theta comma pi plus phi. And this means the cos theta in the argument for PLM gets replaced by cos of pi minus theta, which from elementary trigonometry is minus cos theta, and the phi here gets replaced by phi plus pi. Now remember that we already have worked out that when you change the argument of PLM z to minus z, it picks up an extra phase factor of minus 1 to the power L plus m. That's the extra sign factor that you get from the change in PLM. Well, as far as the phi part is concerned, you have e to the im phi, but on top of that you have this extra factor of e to the im pi, and e to the I pi being minus 1 from Euler's beautiful equation, you get an extra minus 1 to the m here. So overall, the effect of parity on ylm theta phi is you pick up an extra factor which is given by minus 1 to the L plus 2m, and since m is an integer, 2m is an even integer, minus 1 to the 2m is 1, so you ultimately end up with minus 1 to the L times ylm theta phi. So the final result that we have here is that the parity of the spherical harmonics depends only on L and not on m, and a spherical harmonic is an even function under parity if L is even, and an odd function under parity if L is odd. Let me now talk about one more property of the spherical harmonics, and this is the connection between YLM and YL minus M. Note that YLM is defined using PLM cos theta, and we already know that the associated Legendre functions for minus m and plus m are connected to each other. So we can actually use that to see that YLM and YL minus m are connected to each other in a rather simple fashion. Let me just point out that the definition of YLM theta phi, which is here, if you put minus m in place of m there, all the m's change sign. So in addition to PLM becoming PL minus m cos theta, the normalization factor in front changes sign, and e to the im phi changes sign as well. So this becomes e to the minus im phi. But let me remind you that PL minus mz is actually minus 1 raised to the m times L minus m factorial by L plus m factorial into PLMZ. So if you take this and substitute this back here, you will notice that the change that had happened in the normalization constant, L minus m factorial by L plus m factorial has changed to this, will be changed back because of this extra factor that the PLM PL minus m connection gives you. Of course, you will have this minus 1 to the m factor, and the only other change that happens is e to the minus im phi has appeared here instead of e to the im phi, which is the conjugate of e to the im phi. Since the rest of the factors are all real, what you have is YLMZ gets conjugated when you change m to minus m with this extra factor of minus 1 to the m. So in other words, if you want to change the sign of m to minus m in a spherical harmonic, all you have to do is take a complex conjugate and then multiply it by a minus 1 if m happens to be odd. If m is even, then just conjugation will do. Now, one reason why this is a very useful formula is that for any given value of L, m goes all the way from minus L to plus L. That is 2L plus 1 values in all. So when you want to tabulate the spherical harmonics, you would have to tabulate 2L plus 1 different spherical harmonics for each L. This equation tells you that you don't really have to tabulate the YLMs for negative m because they're taken care of by this relationship if you know the YLMs for positive m. There are many more properties of the spherical harmonics which can be listed out here, but there is really no point in listing property after property at this stage. We will discuss some of those properties when we will have occasion to use them, and we will have plenty of occasion to use them. Let me just draw this discussion on spherical harmonics to a conclusion by listing out a few of the lower order spherical harmonics. These are the ones which we will meet very often in various calculations. So starting from the definition that we have of YLM theta phi and helped along with this Roderick's formula for PLMZ, we can easily figure out the PLMZs and YLM theta phi's for various values of L and M, and I'm just going to list down the smallest few. That is those for the smallest L's and M's. P00Z obviously is 1. By the way, as we have already seen, PL0Z is always PLZ. So that's just the Legendre polynomial. And Y00 theta phi has a 1 here. e to the im phi is also 1 because m is 0. This factor here is also 1 because 0 factorial divided by 0 factorial is 1 by definition. You have a 1 here, so it's just a simple constant root over 1 by 4 pi. You may be wondering why this is root over 1 by 4 pi instead of something simpler like 1. But remember, if you take the mod square of this, which is just the square of this in this case, and integrate over the entire solid angle, you end up with 1. Since the entire solid angle is 4 pi, this root over 1 by 4 pi is exactly what you need for the normalization. Well, let's move on to slightly less trivial examples. L equal to 1 has 3 different values because there are 3 values of m, 1, 0 and minus 1. And here they are. They are listed here. P11z is minus square root of 1 minus z square from the definition. P01z is just z. P1 minus 1z is square root of 1 minus z square. Now, if you just use the fact that square root of 1 minus cosine square theta is sine theta and plug in the formula so that you can find out all the other factors involved, y11 is minus root over 3 by 8 pi sine theta e to the I phi. Y10 theta phi is simply cosine theta up to a normalization factor of root over 3 by 4 pi. Y1 minus 1, well, I didn't really have to list this because I have just told you y1 minus 1 can be found from y11 just by taking a complex conjugate and changing the sign because m is odd. So that's how these two things are related. For L equal to 2, I will just list the values for m equal to plus 2, plus 1 and 0. The ones for minus 1 and minus 2 can of course be found out using this standard formula that we had just talked about. So if you use the formula for the Legendre functions, you can get these, and then the spherical harmonics follow. Y22 happens to be sine square theta e to the I2 phi. Y21 happens to be sine theta cos theta e to the I phi. Of course, there are normalization factors in front. And Y20 is 3 cos square theta minus 1. Just to drive home the point again, Y2 minus 1 is actually plus root over 15 by 8 pi sine theta cos theta e to the minus I phi. And Y22 is also plus root over 15 by 32 pi sine square theta e to the minus I2 phi. In the case of Y2 minus 1, the sign changes from Y to 1 because of the fact that minus 1 to the m is minus 1 for m equals 1. At this stage, we have said all that we wanted to say about the angular equation which follows when you try to solve the time independent Schrodinger equation for central potentials. In the next lecture, we will start discussing the radial equation for some simple systems. The hydrogen atom, of course, is one very important example that we will discuss. So until then,